from the lecture notes. It is the definition of the four kinematics and the definition of four DH parameters. So this is the coordinate setup for the dynamic robots, and if you follow the rules, you can set up differently, but I set up like this. And some of you, the x6 is pointing downwards, and it's fine. Then you will just have 100 degrees rotation on this. So we'll upload this solution to Moodle's and Facebook group, and you can check your answers. And to the definition, and this is the DH parameters, and you can generate the parameters. And this is the general matrix function for the DH transformation matrix. And you just plug in all the parameters. And you can get from the 0 configuration to the 6. And for the four kinematics, you just multiply all the metrics, and this is by using MATLAB. And the last question is, this is the input angle, and through the input angle, this is the transformation matrix you get, and you can express the last three column as the last column as the vector, position vector, and this 3 times 3 matrix is the rotation matrix, and or you can express in euro angle. And I'll quickly show you the math function. One, you can just input all the parameters and you plug into the general function. Or you can just like using the stupid method, you can just write down all the transformation metrics. And this is from the transformation for the second configuration, and third, fourth, fifth. And by this, you can check whether your answer is correct if you have some mistake. And we also can, using the plot function, and do the figure. So I can show you. And for the input angle, if it's 0, and you can see this is the manipulator, and this is the link, and these are the joints, and this is the aim factor orientation. So by simple plot function, you can draw the robots. So it's like using the plot 3, you just plot all the lines and all the points. And by the way, if you want to check whether your transformation matrices are correct, you can check all the matrices by, like if you want to check the first matrix, Then you can check whether the coordinate system, the orientation, and the position is correct. And you can also check the second one. So by checking this transformation matrix with your geometrics of the robots, then you can check your answer. If you find out your answer have some mistake, then this is how you can check step by step. So you can check the first one, then the second one, and third one. If all are correct, then the final answer will be correct. So I think this is for the solution for the homework 2. And we'll have the presentation for the proposal today. And I think each group will have 10 minutes for the presentation. And I think you can start your presentation. So which group want to start first?
I think we need to start off.
Okay. So please, group one, please come up on the stage. Guo Jiahong.
Good afternoon, everyone. I'm the speaker Liu Yanrui, and my teammate is Shi Yinghua, Guo Jiahong, Wang Yishen. And today we are going to talk about the transfer rate, and this is our proposal. And we are going to talk about the transfer rotation robot.
Guys, please control your voice.
We are going to talk about the transfer rotation robot, very more simple and in the literature review, we will talk about the previous research, and in the problem described and objective, we are going to talk about, we'll form the problem and we'll talk about what we are going to do. And in the previous study, we'll show some study we have read, and final schedule and reference. So what is rotation robot? Basically, it's like this two picture, and this is given, or you can call it long arm egg. And rotation is a motion like this two picture. The given will grab the branches or anything they can grab. And many people in this field study this motion, and we are working on this dynamic mathematical model and quantum algorithm. And the most famous team is led by the Professor Fukuda, and this is their research video. And inspired by this idea, our lab developed this kind of transfer rotation robot. And transfer means it's like, unlike the previous videos, is going this direction parallel to the environment. And if you you see the this picture, unlike the Facebook Kuda's research, it's like our moving direction is their moving direction is parallel. Their moving direction and the environment is vertical, and our moving direction and the environment is parallel.
Besides background and challenge, the greater design of the TRPR3 robot used a servo motor to drive the moving part, as shown in the second diagram. After the moving part combines with the fixed part, a DC motor starts to move the control line, as indicated in the diagram. In the previous design of the TRPR2 breaker, manual scrolling was required to reset the line. This new design solves the issue of resetting the control line and provides both a quick relaxing function and grabbing force. Breaker design details: stable braking force. To maintain stable braking force, a force sensor was installed in TRPR3. It continuously ensures the gripping strength during swings and adjusts the motor's input to ensure a consistent grip, fixed and stable relax mechanism. The new breaker design features and improves relax mechanism that ensure quick and reliable opening during flight without intended relax. Automatic reset function. The TRPR3 breaker was an automatic reset mechanism integrated with the control system, allowing continuous operation without manual intervention after each cycle. Result and issue: more stable braking force. The installation of the force sensor improves the stability of the braking force, ensure more consistent performance during dynamic motions. Faster relax speed. The design relax mechanism ensures fast relax time, allowing the robot to transition quickly between the heads. Reliable automatic reset. The automatic reset function in the breaker system ensures reliable operation by resetting itself after each reset, enhance the intelligence of the robot. Expose right handling issue. One notable issue encountered was that the exposed right hand to tangle during dynamic movement disrupt the robot's operation. Insufficient braking force. Despite improvement, the gripper operation is experiencing insufficient braking force, especially during high-speed transition leading to unintended relax.
Okay. Another robot. In this robot, design background is the challenge. Response delay. Its gripper experience delay in response time, which impacts its performance and the operational efficiency. And the electromagnetic environment limitation. Its gripper can only operate effectively in environment where the surfaces are compatible with electromagnetic extraction, which is severely limited is using in environments with non-magnetic material or very low surface. And grip design detail. The current design of this gripper involving electromagnetic will allow for a rapid switching between gripping and releasing action. This design aims to employment response time and flexibility for more complex and dynamic tasks. Result and the issue. Despite the employment in design, this gripper still face some limitation, particularly when handling tasks that require greater precision or adaptability. Our problem design described. In the previous work video, we can see our plan use a simple way to increase the clamping force. For example, using the C-clamp or magnetic grip. However, this approach often applies insufficient clamping force for more challenging tasks. The lack for the clamping gripper straight limit the system's effectiveness in holding objects securely under varying conditions. Our object. To address this issue, we aim to redesign this grip to work on our leg pressurization robot. The new design will focus on enhancing clamping force and expanding the usability beyond magnetic employment, ensure adaptability to a wide range of surface and material.
Okay, in order to request the gripping force of a gripper, we refer to other study focused on improving grip strength, and our goal is to combine those other studies that have the technique that will increase the gripping force. And we see the first one we found was based on microspine technology. This technique used densely packed microspine inspired by inkjet curves, designed specifically for gripping groove surface. Okay, in this design, the microspine are key to providing the necessary adhesion for a robot to climb. The spine latch onto tiny surface in regularity, creating friction and a secure grip. Each spine is made from hardened steel, ensuring durability and ability to withstand repeat use on roof surface. The spines are arranged in tails, with each tail holding 16 spines, supported by a lightweight 3D print for flexibility and S for manufacturing. And the design of a pump is optimized for climbing. A key feature is the load sharing system achieved through a pulley mechanism, ensuring the load is evenly distributed across all tails. This allows the robot to grip surface more securely, even on uneven terrain. Each tail also has its own spring mechanism, which returns the tail to a natural position when not engaged, keeping the pump ready for the next grip. Several innovating techniques are used to enhance gripping force. The pulley differential system distributes the load even among the tails, ensuring no single tail is under excessive pressure. The spring mechanism allows the tail to engage with the surface using minimum pressure, reducing the energy required for each grip. Additionally, the high spin density is 19 spine per square centimeter, significantly boosts adhesion, ensuring a firm grip even on roof or uneven surface.
Okay, the software actuator design relies on shared memory alloy forwards, which contract when it's providing flexible bending capability to adapt to various object shapes. The rigid layer ensures structural stability during bending and the non-uniform cross-scale design allows variable curvature for enhanced adaptability. The source actuator is driven by SAN wires. When hit the SAN wires contract, causing the actuator to bend when pulled. The actuator returns to its original shape by adjusting the heating current. The bending angle can be processing control and the cooling system reduces recovery time, improving operational efficiency. Okay, this is our schedule. We will consider the market research and the methodology and the robot design from October to November, and present a result in December. This is my difference. Okay. Thank you.
Thank you. I'll go first. I have some suggestions and some questions. Let me talk about the suggestions first. The style of every one of yours presentation is not very good. Every one of you prepares some sheet with some paragraph. You try your best to read them, but what you said has no connection with your slide. So it's very difficult for us to realize which part are you talking about. It's like you are just a reading machine. You have no soul on your presentation. So you need to practice. And my recommendation is, if you want to use this is so-called a cheat sheet, right? If you want to use a cheat sheet, it's okay, but you don't read the whole thing. You can write down some notes. For example, you want to say about 5 different things, write down, and don't read exactly. When you do that, you are not a good presenter. Talking your own way. In the future, you may be joining some international conference and present in English, or maybe in the future you find a job, you need to present in English. Or maybe you need to present in Chinese, but you still use the same way, then you will find bad results. Okay? So that's my suggestion. Questions. I don't see what you are proposing. I think the most interesting part probably is the micro spine. Can you show the micro spine? And you mentioned the micro spine will increase the friction. Yeah, but friction doesn't mean clamping force, right? Am I right? Clamping force is like the normal force.
Yeah.
The friction is the interfacial force.
Yeah, but our like previous research, our problem is like
I don't care about previous research. I care about what's your opinion on friction created by microspine and how that can enhance clamping force.
Yeah.
I'm not asking about previous research.
Yeah.
So basically, it's like it depends on the environment.
But friction force is an interfacial force.
Yeah.
It has nothing to do with the normal force. So if you want to clamp harder, maybe with a stronger motor, or I don't know why, that could enhance the normal force. But what you propose is 2 different concepts.
Maybe our presentation, that you like misunderstanding. Our goal is like want to like increase our like gripping force.
Okay. How?
Yeah, the gripping force. So we use.
Tell me how.
You mean
how do you propose to enhance the clamping force? By stronger power or how?
Sorry, you're
How? H-O-W.
Yeah.
How? 怎么达到更强的夹持力 ？How do I need to use Chinese?
Yes, so I will just use like maybe combine the also like a microspine and like the another technique like
What technique? I didn't see anything indicating how you enhance the clamping force. So do you want to increase the friction or do you want to increase the clamping force? I think there are two different things.
Yes.
They are related, but they are two different concepts.
Yes.
You can have very strong clamping, but poor friction, so slippery. Or you can have very strong friction, but low clamping force. Because there are forces in two different directions.
Yeah.
They are related, but not the same thing.
Yeah.
Which one is your goal?
Our
Stronger clamping or stronger friction?
stronger friction.
Then you need to present clearly,
Okay.
so I don't misunderstand.
Yes.
Okay.
That's our.
So later on, when you make up your proposal, think clearly about your goals.
Okay.
Don't rely on ChatGPT or whatever resources. Think clearly, write your own words.
Okay.
Secondly, why you present soft actuation? I never see anything that is related to soft actuation. In the last part, how is soft actuation related to what you want to work?
Because we present like this technique is because our goal is want to increase the breathing force, like the friction and breathing force.
But that doesn't mean you need soft
Yeah,
actuation.
so we just search like the
So
like
are you trying to find possible ways for actuation?
yeah, we will just find we just search like every keyword about how to increase the friction or increase the driving force. And we also see the technique is the soft this technique and also
Because SMA is usually very weak in the strength. So if you use SMA, you are providing weak clamping force. And your soft actuator usually is strong when you have pressure. Air pressure is strong. But still, if you use a motor, it's much stronger. So what you're proposing in the earlier slide may not be tightly related to this slide. Usually people use soft actuator because they want softer touch. They want to grasp the fruit. They don't want to damage the fruit. So they want strong enough motion, strong enough actuation, not super strong actuation. And right now you are mimicking a monkey's motion.
yeah.
You need very strong, like a force in the palm. So maybe those are not helping.
Okay, we will fix it.
So basically, in your today's presentation, I don't see anything that is a good proposal. And it's not clear what you are really working on. Your group didn't pay enough attention on this proposal. And also, this topic has been presented so many times from your professor's group. Every year, your group focuses on this same topic. So it's a little boring. So unless you can bring some new ideas, otherwise it's the same thing for me year and year and year. Okay, so please go back and think clearly.
Okay, thank you, Professor.
So one of my suggestions is that you are very structured because you can go to your problem statement page. Yeah, so from the this page and the previous page, you didn't really state your problem. And so just now I have listened to your presentation. You have said that you want to grab like various situations or various conditions.
Yep.
And usually if you have a problem, then you need to write down your problem clearly. And then you need to give your proposed solution. And I didn't see your solution. And you just jumped to a microspine. And like Professor told me, we didn't know what the microspine are used for, and we didn't know what the self-actuation are used for. And so you need to present your proposed solution. And through the proposed solution, you will have your method to really do your solutions. So you have to jump a lot of steps. So you need to propose your problem clearly and your solution. Then what are the methods you can achieve your solution? And then through the method that you can have this microspine, or you want to use self-actuators. So like if you want to like for like some solutions, like if you want to grab normal force, then that's why Professor Lin asked for the friction. But if you want to grab the more vertical condition, then maybe you need frictions. So that you need to state what is the problem and what are the solution and your method. And from this, I didn't get any sense of what the self-actuators are used for. And from your initial review, so your previous study, I said that you need to release the time you want to release that page 7. And also you need to have your page number. And so like from 7, so it's like for the second one is you have quick switching between briefing and releasing. And so do you think your method can achieve quick switching? Because I know that you need to release as fast as enough to have the gravity force. So do you think your proposed solution can achieve the quick switching?
By using this,
again, is that microspline, you have friction, and you'll know that the friction will have some delay because like it is not like a very strictly normal force you can just up and out. So you have normal force and you have friction. So the time you want to get released will increase. And another thing is that if you're using the soft actuator, it is like through air pressure or through like you have using a straight mirror alone. And that is the disadvantage of that is the time consuming. So if you are using that, you will take a very long time to release your grip. And if you're taking a long time to release, will it still satisfy what you want to do? Can the robot still do this motion? So can the robot still do this motion? So because like if you present a solution to, I mean, if you like come up a new methodology of this robot, but it has agreed, you cannot. So can the robot still do this motion?
If the robot is fully actuated, I think it can reach, but it's under actuated.
So maybe you can really go back and come up what is your problem and what is your solution, proposed solution, and to the solution you can generate all the method can achieve this solution.
Hello everyone. Today we will present our proposal about our robot about the design and performance analysis of a 3D printed quadruped robot wheels. And quickly through our structure, we will start with our problem statement, then go ahead to the background and related work, previous work, what we're relating to our object, the task, the growth, and our contribution, and at least and the last one is our reference. The problem status, we had some research and I want to know, okay, how we can solve maybe a problem, and we want to develop a robot dog that navigates through an environment and what is difficult for a human and machines. And the current system what's at the moment on the market is, for example, the Boston Dynamic called Spot, who's most time for industrial works, and it's really expensive. And the strength and weakness of current robotic dogs are the mobility and obstruct avoidance and the limited of facility. And what I was saying already is the Boston Dynamic is really expensive. Not everyone can use them, and most of the time for smaller companies or for private use, it's not affordable. And our goal is to develop a cost-efficient robot dog with wheels, and diverse that we can use in diverse environments. And it should also make autonomous navigation accessible at smaller business and research terms. So for our background related work, we have here two examples. The first one is the Boston Dynamics. It can walk automatically and is really good for the industry, but it's really expensive. Then the second one is developed from MIT. It's called Mini Cheater, but it's just for studies and research, so you can't use it in the real world. Then figure 1.4 is the Under 3 Go 2. It's kind of similar to the Boston Dynamics. You can also walk and detect objects and walk around and climb. It's way cheaper. And then there's also kind of another generation, the other Under 3 Go 2 Y with wheels. So you can also drive through certain environments. And we have also one it's called it's developed from Sony. It's Audio. It's more for detecting how people are acting, and it's more like a social robot, and it can see how people are acting and can do some fun tricks just for fun. And the last one would be the V1 robot dog. It's also with wheels and can also climb stairs. All right, now I will hand over to Ashley.
Okay, good afternoon everyone. This is the section of the previous work. Previously I shown the case study I worked on the underwater robot. In this project I have some similarities in the quad robot with my previous project that I have shown in this one. This is the This is our robotic dog is autonomous, which is similar to the previous one. This is background in autonomous systems. Previous was focused on autonomous underwater vehicle with similarity to quadrant robot, including sensing, control, and autonomy. What does it mean by quadrant robot? The first question came in our mind. The quadrant robot is basically designed for the mimic the walking pattern of animal. It is a four-legged robot which mimics the walking pattern of animal. There is a key technological element which is common in the robotic dog and our underwater robotic. Advanced sensor system and control algorithm used for autonomous navigation and environmental sensing in EUV. Integration of multiple degree of freedom for precise control and agility of both the UV and robotic dog. What does it mean by the degree of freedom? Degree of freedom is basically defines the number of independent motion that shows the complete configuration of any system. That's the degree of freedom. In the previous underwater robotics and this one, we have used the multiple degree of freedom. And the control architecture. And in UVs, we have used the Pixhawk and JSON Xavier controller for the real-time sensing, making object detection and localization. In robotic dog, we are not going to use the same as the previous, but we'll use almost similar control system for adaptive movement and obstacles avoidance using real-time sensory data. And we have the same condition as the previous one, environmental sensing. In AUV, employed pressure sensor cameras for object detection and terrain mapping. In robotics dogs, we utilize proximity sensor, cameras, and environmental detectors for adaptability in sensing temperature, humidity, and obstacles. There is some challenges while I was making the underwater robotics and this one. While I was work on the AUV, I faced the challenges that I mentioned here. AUV operated under hydrodynamic constraint. Robotic dog will balance mechanical efficiency with environmental adaptability. Computational fluid dynamics for AUV is similar to how finite element analysis will be used to optimize the robotic dog structure and movement. There are some insights from us. Adoption of principles from underwater exploration to the land-based autonomy, enhancing the reliability, adaptability, and performance of the robotic dog. Jason will move the floor.
Okay, and that is our test. First one is 3D printing technology and movement design. First, we use the material for 3D printing is for PLA and ABS. PLA is lightweight and rigid, and we want to use PLA to make our non-load bearing parts like the outer shell and internal support. And for ABS, it's stronger and more durable. And we want to use this material to make our load-bearing parts such as leg structure and joint. And for our motion design, we use each leg we use 3 servo motors to let the robot dog to move. And for kinematics and inverse kinematic, we conclude joint angles to control precise movements such as walking, turning, and obstacle avoidance. And in inverse kinematics, we use to determine the required joint angle to reach target positions, ensure across navigation and stair climbing. And the second one is obstacle avoidance and hardware components. And for our obstacle avoidance, we use an ultrasonic transducer for real-time detection of obstacles. And for our hardware, we use Raspberry Pi, motor shaft, battery, and DuPont line. And this one is file. And our file we will put on the robot dog's leg to And the last is structure, assembly, and project goal. And for our structure assembly, we use screw and nuts to securely assemble the robotic dog body and joints. And for our project goal, we develop a cost-effective robotic dog with the ability to walk, climb stairs, and rotate.
So we discussed some approach measure for this robot. So first we talk about the center of a great trajectory playing measure. So focus on ensure the stable of the robotic dog it can work balance. So the key concept here is the supporting triangle formed by the remaining leg. When one leg is swinging for the robot to maintain balance, the projection point of the COG must remain inside this triangle. So the evaluate the stable of the COG trajectory, we use the long dynamic and stable margins. The condition for stable is SM while bigger than minimize for D1 to D2. So where D1 and D2 are the distance from the COG projection points, the suppose edit. So as long as the COG projection points meets the condition, the robot will remain stable. This approach is good for maintaining balance during dynamic movements.
Next, I will explain the method we use. Approach swing, neck, hook, and trajectory technique. Our objective is to design the swing, neck, foot, and trajectory to ensure smooth movement of obstacles. The aim is to create a path that allows for field motion while avoiding abrupt change in movement. Planning steps. Then introduce the planning steps. Initial planning, we utilize qubits by the function to ensure smooth transition between trajectory points. This helps to snap the path in a smooth and continuous manner. Path point planning. For each point along the trajectory, we calculate the path using the qubits by equation. This equation ensures that the movement between points is smooth. Optimization goal. Next, explain the optimization goal. We define the object function x is minimum fx to minimize the smoothness and obstacle avoid function. The purpose is to ensure the swing leg moves smoothly and avoids obstacles during its motion. And we addition contrast positive acceleration. This contrast reduces the system from exceed predefined acceleration bounds, ensuring safe movement. And smoothness contrast. This contrast limits deviation between trajectory points, ensure continuous and smooth movement.
This is the conclusion of our project. We have to aim to develop a cost-effective robotic dog using 3D printing and standard components. And the second objective is the incorporated versatile movement like walking, rotating, stair climbing, and obstacles avoidance for enhanced functionality. And the third one is the demonstrated the potential for real-world applications like rescue operations, surveillance, and education. And these are our references. If you are interested, go through these references. And thank you.
Okay, so we go to the question about SLSM. So in this figure, I can see D1 and D2, but I don't see where is SLSN. Is it a number? So who got this part? From the paper or from where? From okay. When you write a proposal, there's some wording doesn't look like what you truly mean in your proposal. It looks like you directly copy some sentence from the paper, because there's a sentence you said the author proposes the SLSN to evaluate the stability of the COG trajectory. I don't think you guys will write a sentence like that. I don't think you guys will call yourself the author. Usually for research paper, the authors will call themselves authors. But you guys are just students from the course. I don't think you will say you guys are the authors, which means this sentence was from the paper, right? So it's okay to learn from something, but if you dare to write it down in the proposal, then you need to truly know what it means. Otherwise, you are just copying things from here and there, put it in here, and just means nothing. And there are some mistakes in this paper. When they define SLSN, what happened to the S, the first S? Right, so maybe when they wrote the paper, there's some missing first word. I just Googled, I think the first word probably is static or something else. Starts with S. So if you get something on the paper, if they make a mistake, you just copy it without thinking or defining in your own way, then it's you can do better. Okay, please go to the cubic curve. Yes. What is X right here? It's a small case X. X. You have a dog. You have a dog, right? What is X for the dog?
The foot and the dog foot.
Coordinate.
Leg movement.
Movement.
Trajectory.
Trajectory. So a bunch of coordinates. You know coordinates, 坐标. A bunch of coordinates. But the whole leg has so many points. Which point are you talking about when you say X? The shoulder point? Look at it. Shoulder point, or the elbow, or the feet. Which point? So when you define math, you need to define clearly. Or are you talking about the center of the gravity about the dog? And how many axes are there for the dog? It's an animal, right? The center of the dog, the center of gravity of the dog probably will be moved in a nonlinear trajectory. And also for the entire 4 legs, they have their own trajectory. To design all these motions is already a very challenging research. So my recommendation is, this is a good research. If you focus on designing the trajectories of the dog, important parts of the dog, please don't build it. You don't need to spend money on buying stuff, printing stuff. Just design the dog by math, by computers. If you can design this properly and figuring out the motion sequence of each motor for the dog. How many motors do you need? 6?
No,
12.
12.
So in the report you mentioned there are 2 motors for each leg. Is it this one and this one?
Yes. And this one is for the what?
For the wheel.
Wheel.
Okay, so 12.
Yes.
So the body is like a box.
Yes.
Okay. So does the legs is the leg moving in a plane? Like four legs moving in a plane? Are they allowed to move transversely?
For our robot dogs, we want to move forward and backward. We use the
How make the turn?
then to make a wheel like this one and this one.
So just treat it like a 2-wheel car.
Yes, and when it have the obstacle to cross it, it can use the leg to cross it.
Okay. Well, but even it's a design like this, there are a lot of issues. You have 4 wheels, and for a 4-wheel car, when you want to make a turn, have you ever seen your car turns? The wheels rotate in different angles. They don't rotate in the same angle. And in your design, there is no way you can make a turn. You only rely on clockwise and counterclockwise rotation of some of the wheels from left and right. So some other wheels may be having slippery on the floor, right? You are not using mechanism wheel, right? You are using regular wheels. So there will be issues. So I think right now the concept is very unclear and many inappropriate parts. But I like the idea of designing a robotic dog in various kinds of legs and wheels, that's fine. And if you want to design certain motions of the dog, and maybe you can define functions like velocity profiles of the motors in each of them, so you will have 12 motor velocity profiles, basically how they rotate with time. So combination of them indicates to certain motion. If you can design something like that, I can, and then maybe simulate by MATLAB or some software to show, hey, if the motors were controlled in this sequence, then my robotic dog will move like this and that. And don't mention jumping. I don't think you can do jumping. So when you propose, please propose precisely. Tell us what you exactly want to work on. Don't claim too much. I think jumping is too much. Right? It's not like you are. I feel like the way you present is like you're trying to get funding from a founder. So you need to say a lot so the founder give you money. But this is just for a course. You propose something you can work on in a month and define precisely. And also in the first part, I think someone mentioned about CFD for underwater vehicle. It has nothing to do with the robotic dog. So they don't even need to be mentioned.
Professor asked, they have mentioned he write some previous work of yours or your professor. So previously I
But
was
it's not related. It's not related to this specific topic.
I was trying to
I mean,
like a
you know,
finite element analysis.
I know, but it's not related to robotic law. So, if you have other experiences that is related to this, then feel free to mention it. And, but that part doesn't flow with your presentation. I would say take it out, take it away. Okay.
Thank you.
So, I think one of your objectives is you want to build a very low-cost robotic dog, and you want to explain that the other dogs are very expensive, but I didn't see the numbers.
Okay.
Yeah. But I mean, if you want to do if this is one of your objectives, maybe you can do some like unique numbers. You need to do the quantitative. And another one is you mentioned the forward and inverse kinematic control. I think it's the page. Yeah, so do you think if you want to do a control, you can do only by the forward or only by inverse kinematics? If you want to do a control?
Achieve target and with good inverse kinematic get back and the degree.
Yeah, so actually it's fine. It's like if you want to calculate the target, then use one of each, then you can type a target. But if you want to do the control, only if you want to do open loop control, then but open loop control you cannot say is control precise movement. So if you want to really do a precise control, you need really closed loop. You need to have the feedback, and if you have a feedback, then the feedback will be the inverse of the direct. So if like you have the targets, then you have a joint, then you sense what is the condition or what you have sensed the information, and by the feedback, then feedback will be the inverse kinematics, and you can go back to the input. So it will be a closed loop. So if you want to do a control, then both the kinematics you need to use. And I know that you have already chosen the servo motors, and maybe you can. So what is this servo motor? What is the spec of this servo motors? And if you have already chosen your motors, maybe you know what is your weight limit for this robot. So because when you're doing the design, so these are the specs that you need to figure it out first. So if you have already chosen a motor, then there will be a limitation on what's the robot you want to design. Even if you are when you do your design work afterwards, and so sometimes we'll build up a design and we'll choose the motor later. Or if you have chosen a motor, then you will have all the limitations of your robots. And then I think is it from the section 6.6? It's all from this paper, from the paper section 17, or all these formulas and all these formulas.
It's from the same paper.
Yeah. So I I think inside the contents, I think you have to say that these folders are get from this paper. Yeah, so we will know that you will reference from some previous work, because during the previous work, related work, you didn't mention about any formulas or any mathematic things or any methodologies of how to control a robot, but it's like coming into your proposed method, then we won't know whether this is by yourself or by you reference from other. So you need to clearly say that. Yeah.
Thank you. My suggestion is forget about cubicle. It's not performing part. I don't think we will even get to that part.
This is our final report on fence working robot. The following are our members. Introduction. Motion dynamic developed the robotic dog in 2005 with the primary goal of assisting soldiers in navigating complex terrain where workers are unable to operate. However, we have observed that current robot dogs tend to fail when encountering trends in ground elevation, which causes instability in the equipment of objects they carry during movement. To address this issue, we plan to design a robotic dog that can maintain a level body level when the ground elevation changes, making it a stable platform suitable for transporting project and vibration-sensitive items.
Before discussing which type of robot most suitable to our requirement, we first learn two types of robot: wheel robot and leg robot. Here is the comparison result. From this table, you can see the leg robot outperform wheel robot in terms of transferability and navigation over obstacles. Therefore, we plan to choose the leg robot architecture. However, in this type of robot, the challenge is the disadvantage is the complicated control theory. It is the biggest challenge for our project. Next, let's take a look at the evolution of leg robot since 1980. You can see the leg robot are becoming increasingly lightweight. And the end of this chart is the famous robot. Spot. The spot is developed by Boston Dynamics
is a highly agile control-based robot designed to navigate various terrains. It is equipped with multiple sensors and advanced control system, allowing to perform different tests such as inspection, data collection, and even opening a door. Here you can see its excellent mobility in this job video. But from this video, we noticed the spark will maintain its body parallel to the ground while walking, but micro adjust its body angle while when driving the slope. So this is the thing different to our need. So we expect our the robot will always keep the body parallel to the ground. So this is the thing we want different to this part. So how to control the robot? How to control a robot? By reviewing the current by reviewing different current literature on control methods, we found that the primary research is to imitate the animal walking pattern and convert the showing data into control algorithm, like this literature. From this literature, it cannot both maintain the body always parallel to the ground. So we plan to use the forward and the inverse kinematic methods directly to control the limb movement and achieve our desired functionality.
Hello everyone. Now I'm going to talk about the goals and intents of our project. Our project goals for this project are as follows. First, we want to ensure the robot can move smoothly, providing seamless motion. Second, it should be capable of overcoming obstacles in its pace, handling uneven terrain and avoiding obstacles efficiently. Finally, a crucial part of the project is for the robot to maintain balance throughout its movement, even under challenging conditions. To achieve these goals, we have broken down the project into three main tests. The first test is to design the mechanical structure, focusing on the legs, motors, and the overall appearance of the robot. This will provide the foundation for its movement. The second test is to develop an algorithm to control the robot. This algorithm will help manage movement, obstacle avoidance, and balance control.
Lastly, we will integrate the system and simulate the robot to test how well it performs and make any necessary adjustment for improvement. Okay, so here's our approaches of our project. The first part is mechanical structure design. We'll use SolidWorks or Inventor. In lab design, we'll create a stable multi-leg structure to enable the robot to work on uneven terrain while maintaining balance. In appearance design, we'll develop a low-bearing platform to ensure the robot can stably carry a load while keeping it stable during movement. And the second part is algorithm development. We'll use MATLAB or Python in this part. In batch control, implement a feedback-based control algorithm, such as PID control, to adjust the robot's movement and maintain balance based on the virtual center of mass. In obstacle handling, device strategies for overcoming obstacles by adjusting the leg movement while maintaining overall stability. And the last part is system integration and simulation, which is the most important part. Motion simulation will use SolidWorks or Inventor to simulate the robot's movement, focusing on how it maintains balance and carries the load on different terrains. In control system simulation, we use MATLAB to simulate the control algorithm and test its effectiveness in maintaining smooth and balanced working. So in motor control, our robot will have 2 motors on each leg, totaling 8 motors. And Arduino will be used for our motor control. The last one is testing and optimization. We'll perform multi-simulations with various load weights and terrains, adjusting the design and control strategy for optimal performance.
Let me present our schedule, the timeline of our project, breaking down in key phrases such as data connection, also design, drawing, axis, and simulator, and drawing, and revision, and rehearsal. So the goal is assigned specifically with allowing the team to follow this schedule. The judge provide an overview of test determination across different projects that ensure this setup program efficiency and ensure the tests are well supported by less than 2 or 3 members, enhancing the quality and project. This is our present. Thank you everyone. Thank you everybody to listen.
Okay, so you guys are lucky to have a team member, Mr. Wu. He probably is so far the best presenter. You can see, you should learn from him. When he presents, he doesn't read anything. He just talk about what he wants to talk about in mind. So please learn from him. Everyone, please learn from Mr. Wu. And he mentioned a very important idea about your proposal. You want the robotic dog to move in a certain way so the platform is always parallel to the ground. So I guess it's for delivery purpose. So it's very clear. He also showed some videos and some literature. Right now, robotic dogs, they move probably doesn't remain flat all the time, because their mission was not to deliver by their body. So it's clear for me, but I would like to know more about how this can be done. And so this will be the question not for Professor Wu, for the whole team. How do you expect this can be done, and what would be the challenge? Why do all the robotics dogs right now doesn't move in a way so the body is flat? Why not? Maybe there's a reason. What do you think? What do you guys think? Or why not just put a gimbal on top of the robot so the gimbal remains flat? That probably solve the problem more effectively.
Actually, we define a spec is our robotic dog can cross the obstacle high, bound, 10 millimeter or 20 millimeters. We have no ambition to apply first step. It's too difficult to us. So first step, we would like to create a robot dog crossing the obstacle with little height and still keeping the body parallel.
So it's just like anime initial D, having a cup of water, but
Yes,
now
yes,
in a
yes,
robotic dog.
Yes.
So I would suggest, because I read the report, concept-wise, I think it's a good idea to have special missions for the dog, but the report doesn't mention too much about the spec.
Yes.
So please precisely define the spec and maybe talk about what would be the necessary method to achieve that. If it's very easy, then I guess it's not easy. But maybe to simulate, not to build it, right?
Maybe, but it depends our
I don't think the time is.
Yes.
So in some of your slides, you guys mentioned you are talking about Arduino, testing, optimization.
Yes.
I think that would be too much. Okay, because building a robotic dog is nice. So I would say do this everything in simulation world. It's okay to redesign and optimize in the simulation world.
So, how many degree of freedom do you expect to your robot?
One day is 2 degrees.
2 revolution joints?
Yes. We robot controller can and robot controller make movement. So there are 2 degrees of freedom in each day.
So it's like also planar motion.
Yes, but just like the cat, the dog, the walking, it will like the moving like this and
move forward.
Yes.
If you have 4 legs which lift, move forward in a planar motion, how do you rotate? How do you turn?
We didn't expand the turn. Yes. But in our imagination, the dog when the dog walks, he always keep the 3 point on the ground. So to keep the place is stable. And the different deck and forward then
So maybe some suggestion is that do you think you really want two regular joints, or you can change one to prismatic joints, or it's still have your goal, still meet your goal? Because I think if one prismatic is just like you control the length, and another one is controlling the rotation, maybe it will be much easier when you're designing these robots if you don't have other, like, you really don't need that two rotational motion. Yeah. And when I read your reports, I think that you have dual selection for your table one in your presentation. So, but I didn't see you cite your table one because it's for
yes.
So the table one is by you or by
aside from a different one.
So I think you need to cite clearly in your reports because your report didn't cite the reference. And your report I also mentioned 6 references, but there only appear 2 citations in the content. So if you have a reference, you need to cite this in your content. And what simulation do you want to use in MATLAB?
MATLAB or Python. Because he is good at Python simulation.
So what's the simulation platform or method you want to use? Okay. So I think you only have 2 or 3 weeks for it to come out the design, the robot design, the final design, according to your schedule. Around 2 weeks. Because I didn't see any your design right now, so now we're
4 weeks.
4 weeks.
This is for 2 weeks.
2 weeks. Oh, okay.
4 weeks.
So right now, what week? Now we are week 7 or
7.
week 7.
Week 7.
So you have 3 weeks left to come out with design. So I think you need to really simplify your design and come out with design fast, because I think we don't have left 2 months before the final presentation. So I think they will have something to do with the simulation. So maybe you need to really simplify your problem and your design.
I think even if the mechanical parts are super simple geometry, such as cylindrical link or like a box, that's already taking some time to figure out the motor control sequence and so on in simulation. So I don't think you need to pay too much attention on detailed design. Just concept-wise, and see if you can simulate those multi-body systems in a cyber world, and also maybe provide dynamics analysis. I think maybe for the dynamics already difficult because each part has a center of gravity. We can predefine the center of gravity of each part, making enough assumptions, and to study the dynamics for every rigid body is nice. Right? So
in my opinion, 3 weeks for simulation maybe is too less. I mean, if you really want to do the simulation, or you only want to do the motion simulation, then in SolidWorks, then will be like 3D. You can do it. But if you want to do the real dynamic simulation, I think 3 weeks is really
We will consider the schedule. Okay.
Thank you. So next group.
Good afternoon, everyone. The project topic of our group is the design and presentation of a full prism of written gas with camera tracking and automatic light source evaluation. Our project will begin with the progress statement, followed by the background, previous work, objectives, and test. Lastly, we will explain the approach, schedule, and reference. Modern individuals often spend long hours working or studying at a desk, requiring proper lighting for their workspace. However, traditional desk lamps are technically steady and leading to functionality, often resulting in insufficient lighting conditions. These lamps mainly provide illumination without adapting to the environment or user needs. Our goal is to bridge the gap in traditional lighting by integrating advanced technology into desk lamp design, improving energy efficiency and protecting the user's eyes.
So, for the background, the need for adaptive desk lamp is because as our workspaces continue to evolve with advancing technologies, traditional desk lamp struggle to meet the modern demands. They often require manual adjustments which interrupts workflow and can lead to suboptimal lighting conditions. To address this, we are looking at integrating automation into desk lamps. This would provide a more efficient and adaptable lighting solution, greatly improving both comfort and productivity. Now let's look at the existing solutions. Products like Philips Hue and Dyson Light Cycle are already pushing the boundaries of what the smart lighting can offer. The Philips Hue series, for instance, allows user to control the light settings through voice commands and smartphone apps. However, these lamps still operate based on preset configurations. They don't have the ability to respond dynamically to the user movements in real time. Similarly, the Dyson Light Cycle adjusts its brightness based on ambient light and time of the day, which is great for energy efficiency and comfort, but again, it doesn't track the user or make any adjustments based on physical interactions with the workspace. On the other hand, the industrial robotic arms produce incredible flexibility and adaptability flexibility. These systems can adjust in multiple dimensions, making them highly efficient for the complex tasks like assembly lines. However, they are too complex and impractical for simple desk lamp applications. So the key challenge then is to develop a system that combines the flexibility of the robotic arm with the simplicity needed for the everyday desk use. Compared to the existing smart lamps, this system will provide a dynamic light adjustment by using real-time hand tracking to automatically reposition the lamp based on user movements. This eliminates the need for manual adjustment, offering a seamless lighting experience. Second, the system will have enhanced flexibility with 4 degrees of freedom, meaning the lamp can move in fully 3-dimensional space. It is unlikely traditional smart lamps that are usually limited to preset modes or basic up and down movements. Finally, the improved user comfort is the key focus. The lamp tracks hand movements to ensure that the lighting remains optimal for any task, whether reading, writing, or using a computer in real time for the user needs. In terms of the related work, a notable study by Yu Ping Liao presented an FPGA-based intelligent desk lamp system. This system uses a vision setup to track the position of a book with a red bookmark and adjust the light angle accordingly. It avoids direct glare by automatically controlling the pan and tilt of the lamp. The system can also controlled remotely via a smartphone app, adding a layer of user convenience. They implemented this technology using Verilog HDL on an Altera FPGA board, providing a solid foundation for a future intelligent lighting system. However, unlike our approach, it doesn't focus on real-time interaction with the user, which we believe is the key improvement in improving the desk lamp usability.
Okay, about objective, our goal is to integrate image tracking technology and automatic light source adjustment to instantly respond to the user's hand movements, providing a flexible and intelligent lighting environment. The key objectives are following 2 points. First, our design includes a mechanical structure with 4 degrees of freedom, allowing the desk to adjust the angle and position of the light source in 3-dimensional space. This flexibility means the lighting of different work scenarios. So, precise mechanical design the desk that can move and adjust its angle freely, offering more accurate and efficient lighting control. The second part of the design is the implementation of automatic light adjustment based on image tracking. This system uses a camera for real-time hand tracking, utilizing image precision technology such as OpenCV or MediaPad to detect the user's hand movement. According to the hand position, the system will automatically adjust the direction and the distance of the light source, ensuring that the light always aligns with the user's working area and maintain an appropriate distance, improving lighting precision and flexibility. By achieving this objective, our intelligent test will effectively and enhance the flexibility and interactivity of traditional test, providing a smart lighting solution that meets modern work requirements. To achieve the goal, we have broken the project down into the following tests that need to be complete. The first test is to reach the forward and the inverse kinematic model of the light stand, which is essential for precise movement control. By developing this model, we can calculate the end effector's position and determine the joint angles needed to reach the specific point. We will start by reviewing relevant literature, especially on robotic arms that apply dynamic parameterization to build the kinematic model for each joint. Finally, we will use tools like magnet Python or MediaPipe to solve the equation, simulate kinematics, and control the light stand accurately. The second test is to reach and select components for the depth and the tracking system. First, we will identify the key function and the technical requirements, such as brightness, sensor precision, and the camera resolution and the frame rate. Next, we will reach components like LED lights, driver circuit, sensor, and the camera model that meet this needs. We will compare options from various suppliers based on price, performance, and compatibility. Finally, we will select the most suitable components and list the specific module and the suppliers for the system. In the mechanical design and the assembly of the 4 degrees of freedom structure, we will first use CAD software to create design drawing showing that all parts of the lens can be accurately manufactured and assembled. Next, we will select the metal rods that are lightweight, strong, and durable to ensure stability and longevity of the lens. Finally, we will choose the drive system to control the movement of the lens stand, ensuring smooth operation and flexible adjustment.
Test 4 is integrate the camera system and programming for tracking functionality. First step is install the camera model on the lens to ensure optimal position and angle. Then we set up the development environment, choosing the appropriate programming language and libraries. So we write a program to implement object tracking functionality, testing and optimizing the algorithm. Finally, we integrate the controller to make the system can communicate and control effectively. And test 5 is research and suitable components for the test lab and tracking system. In this test, we need to conduct various system tests to ensure that the light progression and light brightness automatically adjust based on user's movement. We need to improve the system based on the test result to ensure accurate response and seamless movement. And finally, we will do user testing to gather the feedback and make the system better. The following is the project timeline, and the chart, the design, the key text, and the schedules throughout the months from September to December. And the dot line is schedule, and the solid line means our actual progress. And this timeline will help us to stay focused and track progress to ensure our test is in. And this is our reference. Thank you.
Okay, so why 4 degree freedom? Please someone tell me. Why not 3? Why not 6? Why not 5? Why not 2?
Because I think I want to learn it can be.
Do you have like a schematic design, like how many referral joints, how many perspective joints? Do you have a conceptual design already?
No.
Then why 4 degrees?
Because this is
It's a lamp. You want the lamp to follow certain target, provide enough light. Then you just need like a control the Euler angle, right? Just define the direction. Then you don't. You just need a depot, two motors. You don't need do you need a three angles? Yeah, you need 3. If you want to control the pointing vector coming from the lamp, you want it to point to anywhere. Just two angles. Then 2 degree freedom.
but I want the lamp can be
Not only rotation but also translation.
yes.
Why?
Because maybe I was I take a book and I go
You want the lamp to follow you?
yes, but in
So it's like the scenario is like you are sitting next to the robotic lamp, and you are reading something.
yes.
You want the lamp to follow you like this.
Yes.
Why? Just provide enough light, or turn on the light. Why not just turn on the light? We don't need a robotic light.
Or maybe I fit the car, or not only for them. It's just a light. It can be
Tracking your motion.
yes.
But why is it important? If it's not important, this is useless. Right? My suggestion is forget about that. Because I feel like this is not a good idea. But similar functionality can be used somewhere else. If you want to build some kind of robotic system that has computer vision aided tracking functionality, it can do a lot of things. Forget about lights. This is what I think. For example, in some of the previous research I saw, in the production line. Sometimes they want to pick up something from somewhere from the conveyor and then put it in a box. So you need to, and because the object in the conveyor is moving, so you may need some kind of vision-based tracking system. So it's like a coordinate matching between the camera and the robot position. That is more meaningful, I think. But if you try to do something like vision-based tracking or vision-based positioning, it's a lot of effort for this course. Because you probably will spend too much time on computers, camera, OpenCV, MediaPipe, but then they are very little related to robotics. This is a robotics course. You should focus more on robotics. I know Takeo is from computer science. You probably is really good in those, but this is a robotic course. So I don't want your group to spend too much time on computer vision. If your proposal is having some kind of simple object recognition from a camera, so it can get some coordinates, and you do something on the robotics side, do more on the robotics side. I would think that would be better for the course. And when you plan on the integration, if you feel like, okay, if we do this, we need to truly implement a lot of things, then forget about it, because you only have like 3 weeks. You have some other courses. Don't aim too big. Because what you are aiming probably is like a master thesis. How can you finish it within 3 or 4 weeks? Yeah, so back to your story. Even though you are using a 4 degree of freedom robot lens to track what you're reading, I feel like to use hand recognition by MediaPipe or some other like OpenPose, it's too much effort. Right? You even study the skeleton of the palm. It's a lot of calculation. It's not like a small computer code. And what you are trying to do is just such a simple thing, aiming on the palm. And there are many other scenarios, such as when you read a book, probably your hands are covered by the book. Then the hand recognition will be poor. You didn't even mention some other situations like this. So if you keep on working on this, you will be trying to solve the issues on computer vision, not the robotics. Okay, so my suggestion is to kind of change the goal a little bit. And it's okay to have camera, robot collaboration. That's fine. But please think clearly. That's what I recommend.
So yeah, so my biggest question is also why is the 4 degree of freedom robot? And you didn't even mention what are the degree of freedoms you want to you wanted to build. And also I like the idea of using the map, and maybe you can because sometimes we know that the light direction or the position are not what we will to, and we want to change the light direction and the position. And one of my thoughts is that maybe you can use it in the shadow play, because if you change the position and the direction of the light, then your shadow will make a difference. So maybe that will be one of the implementation situation. And So I think the first thing you need to define what is your problem, because although I like the configuration of the lamp, but the problem is very weak, and you need to define what is the problem, and to solve this problem, how many degree of freedom you need to use. You want to change the position, or you want to change the direction, and how many angles you want to change, and what x, y, z depends on how many axes you need to do the translation. And yeah, I think that this is the main problem of this proposal. And because and the other thing is that if you want to do a computer vision, then it's fine. But you can set up a situation like we already know the answer of the computer vision. Like if you want to do the hand gesture recognition, then we can tell that we already know the hand gesture is 2. Then what is our robots? What will be our robot doing? So like this, then you can jump over the computer vision parts. Yeah, so you can focus on the robotics. And I think maybe you can just go back and think about the problem, and like when you do a design, the degree of freedom, the sensors, these are the priority things you need to define. Thank you.
Professors, everyone, good afternoon. I'm Ben, and today I'm going to representing my team to introduce our project. The title of our project is a 6-leg robot for adaptable terrain navigation. Before we start, I want to present you our outlines today. First, we will have an introduction, and we're going to talk about the objective we want to achieve, and then the method we use. We already have some progress right now, so we will talk about it after. And then some potential issues are identified, and we will have a discussion. So first, we are the third group today. Let's speak about the working robot, right? So nowadays, multiple research studies are focusing on the locomotion of the robots, while a wheel or jack robot can move fast, but encountering challenge in uneven environment or terrain. So the solution might be walking robots, which can be categorized into multiple classification. So by the number of legs, we can have bipedal robots, which have 2 legs, tripod robots, which has 3 legs, and then quadruped robots, which has 4 legs, and our subject today, 6-leg robot, hexapod. By contrast, a hexapod can offer following strengths. So first, compared to a wheeled or jack robot, a walking robot is an easier solution for various
environmental movement without using any other wheel or other configuration. And compared to other leg robots, a 6-leg robot can easily maintain balance and stability while traveling on an uneven terrain. Third, we can apply diverse gait patterns without sacrificing any stability, or we don't need to consider the center of the weight of the system during the uneven terrain. And then let's talk about our objective. Our primary objective is to design and fabricate a hexapod robot with adjustable locomotion capabilities. To do so, we need a real-time obstacle detection and a terrain classification system. This will allow our robot to perceive and recognize its environment in real time. According to the result of detection, the robot can perform respectful actions to adapt against the terrains. This will require the integration of kinematic analysis, mechanical design, sensor perceptions, and mechatronic control to facilitate the whole project. This will be a great practice of our theory we learned this semester. Right? To achieve a larger workspace, we will use an insect-type articulated leg design. With the help of 3D printing, we can iterate the design quickly. And while using 3D printing, we can utilize the lattice structure to reduce the whole body weight. Also, the leg will be arranged in circular area so that the robot can turn around without turning radius. And we already have a preliminary design of our robot leg, and as you can see. So first, we have this joint 1, which we call it a hip joint, and then the joint 2 is a knee joint, and then the joint 3 is an ankle joint. We use 3 servo motors to perform 3 degrees of freedom on every single leg. So the first joint, it rotates about the vertical axis, and the following 2 rotates about the horizontal axis. We have already initiated a model of the system. From the top view, we simplify the model and use trigonometry to solve the hip joint variable. So we can know how much degrees we want to achieve a certain point of the hip joint. And then on the side view, a single leg model is constructed by the position of the end effector. We can use inverse kinematic analysis to derive the hips ankle and the hips joint and ankle joint variables. So next we have an ideal trajectory of the end effector of the leg. As you can see, the animation has been simulated. This will exist as our target for our following prototypes. So next we will try to check our single leg model to see if it matches the trajectory, and after verify on one leg, we will duplicate the result on the other 6 legs. So next, let's talk about the obstacle avoidance. Regarding the obstacle detection, we plan to use ultrasonic sensors as a cost-efficient and reliable solution with consistent performance under variable lighting conditions. So, as you can see the animation below, in our concept, there are 3 types of obstacle scenarios we think you will encounter. The working principle of the obstacle classification is when the sensor detects an object, the robot adjusts its posture by lowering its body. Let's see the animation again. So by the position change of the sensor, the different scenario will be recognized. So the first scenario, this one, involves a low tunnel that the robot can pass beneath the object. The robot identifies the tunnel when it detects the obstacle suddenly disappear. So it will detect the obstacle first and then no obstacle. So you will know it's a tunnel. And the next scenario will be upward slope. As the robot encounters an obstacle, it checks by lowering its body, right? Just so I say, and receive a number from the sensor. When the number reduces at the same point, the robot stand, it recognizes it as an upward slope. The third scenario involves a solid object where the detected distance remains constant. So the robot will choose to move aside to pass by the object. So with the conditions we mentioned, we have designed and control flowchart with our logic test, so that the robot can autonomously, when we program it by this flowchart, it can autonomously classify the object and choose the way to cross the object. Okay, so then we also generate the Arduino system diagram layout. In total, we will need four ultrasonic sensors, and then we need 18 servo motors for 6 days, 3 each one, right? So 18. So the servo motors will be NG995. And we use Arduino board to control the whole system. Next, we have a clear plan that describes in Gantt chart. So as you can see, our time distribution is not that compact. So we can do the task one by one, and we don't need to deal with a lot of objects in short times. And then some potential issues have been pointed out. Right now we are having a discussion and we want to share this with all of you. So first, while encountering a step lower than the sensor platform, how do the robot detect the obstacle and perform the respect gate change? So a potential solution will be an ultrasonic sensor that's placed in front of the robot and 45 degrees downwards to compare the signals with the horizontal sensors. So there will be, maybe will be a fourth scenario. And then second, how to determine if it's an obstacle. What if there's a sudden move or just a fly pass by, right? So our potential solution is when the ultrasonic sensor detects an object, it must maintain the detection for a certain period of time, maybe a delay of 0.5 seconds, and so that it can confirm it as an object, as an obstacle. This prevents the sensor from mistaking lag or something move fast by as an obstacle. So that's our presentation today, and thank you for listening, thank you for your attention, and Professor.
I have one question about the basic curve. Can you show the slide?
So why did you choose the quadratic one, not the cubic?
We use the Bessel curve because
my question was, why did you choose the quadratic one, not the cubic one?
okay. Because we choose the Arduino to compute the inverse kinematic. So
My question was, why quadratic, not cubic?
So right now, our focus is on the detection and the classification of the obstacle. So we just use projection to simplify the.
No, my question is about this. My question was about the equation you chose. Quadratic means second order. Why did you choose the second order equation? Why not the third order cubic? Because usually people use Bezier curve, they use the cubic one. But you learn from the reference 19, right? Yeah. And you write a code for it. Yeah. But usually for Bezier curve, people use cubic, not the quadratic. So that was my question. Why second order? Why not third order?
because when I'm coding, I think second order is easy to code. Yeah.
So if you
I
Google
yeah.
for Bezier curve,
Yeah.
or there are some other curves such as there are some other ones, Hermite or something. They're usually cubic ones.
Okay.
If this is enough, of course, it's fine. But you're right, it's easier. You only need 3 control points.
Yeah.
For the cubic one, you need 4 control points. However, it seems like you want to have some scenarios for more dynamic motion. So I'm not sure if this cubic motion is enough. And do you really need to move along the curve? You can define 10 points.
Yeah.
And you have kinematics, inverse kinematics. You don't really need to follow this is so-called the parameterized curve. You don't really need to follow. And of course, if you want to make things simpler, it's one way.
Okay.
So please go to the block diagram. You have multiple boxes. Yes. So over here, I am a little confused about the checking at the left lower corner before stop. You mentioned about moving or not. What do you mean by moving or not? Right there. Before that, you said move forward. And over, right here, you want, so no obstacle, let's move forward. And then you have a check, right? If you already decide to move, why some kind of check?
So for this checking point is for the controller, for man controlling message. So it will check whether we send a moving mission or we send a stop mission for the.
By the person?
Yes.
Okay. So this is very confusing. So there, like this part is information from sensors, and this is from whether a person assigns some kind of motion. Don't you think it should be reversed? Usually, manual assignment goes first. For example, if you assign the controller to do something, that's where you start. Your manual assignment triggers the system to move. why do you need to check detection first earlier than manual? If there's no manual request, you don't even need to check anything surrounding. So I think the order is a little confusing, and also you're mixing manual request and environment detection in a diagram. It's okay, but you need to specify clearly. Okay. Do you plan to build this robot?
Yeah.
Really?
We were planning.
Because last semester there was one group. They truly built Arduino-based 6-leg robot, and didn't go too well because the time is so limited. So it looks like a talk at the end. Basically, they also spend a lot of time on how all the motors should be controlled in Arduino. And they design certain sequence so the max can be moved in certain sequence. For me, it's like, well, do you really want to do that? So please think about it, because if you start, that probably is not something that you can finish within a week. So you probably will spend 70 or 80% of your time building it. And it turns out not, like I said, you will be prepared. So I like the idea of having a mathematical model for each lab and scenarios of how the movement should be defined for different scenarios, such as tunnel, wall, or slope, because they are more theoretical. You can define certain control schemes for different scenarios, and that doesn't cost anything. So that probably will be an easier choice for the course, and you can spend more time on the theoretical part. That's what I think. Unless you guys can work as a group pretty nicely, like okay, this person do this person do that, this person do this. So you can do things in parallel. That may be that could be another choice. But when you guys do that, usually someone carry the burden. The other guys just do less. Right? So please figure out.
So the meta function, so do you generate the meta function through your kinematic model? Yes, so in figure 7, do you generate this trajectory motion through your kinematic model?
Yeah, just follow kinematic.
So because I think there's some, and still, so you didn't have your coordinate system in your figures.
Is it 4 kinetics?
Yes, we calculate a base curve and.
But the base year curve is the trajectory for the handicap.
So.
And then you reversely compute this inverse kinetics.
Yes, inverse kinetics. I know the theta and know the theta and put into
so
the
you
forward
didn't answer
kinetic.
right. You actually use inverse.
Oh, okay.
And then you use it forward to generate the graph?
Yeah.
Okay. So because I see your transformation matrix, maybe you can check it whether it's correct. And I also didn't see your coordinate system, so I don't know what's your coordinate system changing. So you need to label all this in your report. And so for my suggestion, do you really need to solve the ultrasonic problem in this project? So because I know when you the more legs you want to build, the synchronization of your motors is more difficult to manage to moving forward. So you already, through your proposal, I think your group already think your robot can move forwards very easily. Or because sometimes if you want to build a real robot and there will be delay, or you need to synchronize all the motors together to move the robot forwards. And if you want to use the sensors, then a real sensor there will need signal processing, a lot of stuff in there. So maybe you can just forget the sensors, and you can just you can have your problem solving. Then you can just define that you want to use the sensors, but this sensor is the ideal sensor. Then you have your situation that. So maybe you can you are facing an obstacle, then you can focus on what are the movement of your robots, how you synchronize the legs, how to synchronize the motors to avoid the obstacle to do the trajectory. Because that will spend a lot of time. Because if you want to go even a straight line, then you need to synchronize all your motors. Then you need to do your research, and you need to do experiments. That what are the synchronization of the motors? And if you want to moving down, your robot is height here, you want to move down, then what are the synchronization of the motors? So I think you jump all these control steps of, so you will spend a lot of time doing this stuff. And I think if you finish all this motion control and or motion synchronization, then I think it's enough for your project. So maybe you want to build a real, then it's okay, but then there will be a lot of challenging. And if you want to do it in a simulator or using simulation, then it's fine. You can think of it. So if some of you really good at doing doing real experiments, then maybe you can do the real experiments. But if not, then I would suggest just do it in simulation.
Okay, thanks.
I agree. I think simulation would be better.
For this, your suggestion is just we need to narrow our problem, right? Either for control scheme.
My suggestion is not building it.
Okay. All right. Thank you. Ow.
你的靠路进去了，加力。
Good afternoon, everyone. We are going to present on the photo. The topic is vision-based rendering pick from learner objects. This is our overview. The focus of this project is to leverage advancements in robotics and artificial intelligence to tackle the challenge of object handling in industrial environments. Our goal is to create a more intelligent and adaptable robotic system that can efficiently identify and pick up objects in clutter condition version traditional methods of rendering. And this is the project statement. One of the most significant challenge in modern industrial robotics is the task of random pin picking. This involves using robots to autonomously identify and pick out objects from the pattern environment, whether objects may be in discovery or partition hidden. The problem lies in the complexity of integrating multiple components, the control systems, the robot's optional capabilities, and the visual perception technologies. Certain systems often struggle to adapt to the variability found in the real-world environment. For instance, they can have difficulty recognizing and grasping objects they are randomly positioned or overlapping. The key challenge is developing an autonomous system to detect, identify, and pick up objects. Traditionally, methods rely heavily on geometric features like depths, discontinuities to identify and locate objects. However, this approach is often ineffective when dealing with planar objects, flat items that lack distinct three-dimensional characteristics in such cases. The advance of geometric features means that the robot's perception system cannot accurately detect or interact with these items.
And then we're going to do the background. The first is about its focus on developing flexible and smaller robotic systems. And the random picking is rarely used but remains a difficult task due to object variability and culture. Here research includes feature-based methods, machine learning, and head-based pose estimation for objects. But existing solutions take robustness in complex industrial environments.
Just focus on addressing trend in production robotics, mentioning especially for or planning objects in cruder environments. Traditional methods often relies on geometric features like difference, but it doesn't work well with flat objection because the feature need for reliable detection. So our main goal is to develop a new solution that can detect and estimate the position of flat and irregular shape objection. We will achieve this by using advanced techniques like deep learning-based instance segmentation, which help the system accurately identify and localize objection even in complex environments where they may overlap. Well, I'm wanting to build a robust particle system that can be quickly deployed in industrial setting. It will be scalable, meaning it can handle a variety of random objects with 3D dimension and visible enough to work with other types of objection too. Most importantly, this system is designed to perform reliable in real-world conditions, even in bumpy or polluted environment. By providing this efficient and versatile solution, our project hopes to improve automation in production line manufacturing,
logistic and greenhouse, offering a practical and reliable way to enhance the robotic thinking test.
For the approach, first we set up how we simulate the clutter environment as we have in the industrial. We introduce a method to extract the 3D point from the 3D image data we have. For the system overview, we are using a denser robot with 6 degrees of freedom with a camera attached to the end effector and a second end effector to pick up this object. And for the configuration of the valuation, as we have the two sizes of the object, so we also have the two concepts to pick up the two cases of the object. For the overall structure of the system, we have the two phases. One is for the offline process, and the second one is for the online process. For the offline process, it included the process that we are reprocessing the data, which have the data collection, crop and resize the image, also labeling the data. And we're going to use the process data to train and to refine the model. After that, we can use that model to feed into the system to extract the 3D information as well as estimate the pose, and therefore we can have a coordinate for the robot to follow to pick it up. And for the schedule, we have mainly 4 parts. Which one is the inset preparation, which is we're going to take photos of different blend objects and we label it, clean it, and also we using mass labeling to prepare the data. For the model development, we're going to use that input to train a learning model that we haven't decided how many neural networks or the specific model. And we also have the implementation and testing for about 2 weeks to testing the system. These are our reference, and thank you everyone for listening.
Okay, so do we know one time late?
Yeah.
Is a senior?
Yes.
So basically, what you presented is
maybe the same approach, not the same because
same picture.
Yes, the same picture.
No, same picture.
This picture for evaluation, right?
Same picture from the paper.
No, only one picture. This picture. Yeah. Because
you didn't mention reference.
Yeah, I listen.
So what's different from this one?
This paper.
It's different from the
yeah.
We don't want you guys to rely on someone else. So what's different?
This one, he used the camera fixed in the base frame. Now I use the camera mount on the robot, and we will track it online. Yeah, but
So
different.
basically, I can.
Yeah, on the hand. And different is he used the kinetic camera, the point cloud is good, and now I use the recent camera. The point cloud, the camera recent point cloud is not full, it's poor. So you need to process something.
I don't want you guys to spend too much time figuring out how to improve the 3D image quality from the device.
Yeah.
So that's computer vision. This is robotics. Robotics course.
Yeah.
So, and it has so many similarity to your lab's work. I have seen multiple of those. So Lei and Professor Lei published some other papers somewhere. I was involved. I saw them already. So I don't want you guys to rely on, it's a little unfair to others. So please focus on, it's a good work. It's a really good work and a very well written document. But it's really hard for us to judge which part is new, which part is old. We cannot recognize whether this block diagram is new or not. How can we know?
I think I will prepare the network and real work, and you can know the difference.
We don't know, because we cannot just go into your lab and figure out, hey, did you do something new? It's hard. So why do you stick with the same device?
Yeah, technically they use a different model.
I mean, you even use the same object. Yeah.
Okay, I will use the other object like 6 milligram. It's okay.
Way too many similarities. It's not very good. It's just a course. It's not a Olympic trying to get a gold prize, right? And you don't need to cause so many issues in the course. And you don't need to aim for journal publication in the course. Focus on something you guys can work on together, learn together, that is related to robotics. We're not asking you to publish a Q1 journal at the end of the semester. Why do you just work on something that is so similar?
For this work, I think design the tool too big.
What do you mean?
And for the design, focus on the design the tool.
The gripper?
Yeah, the gripper. For this proposal.
I didn't see anything about the gripper.
I mean the feature.
You want to change a little bit and focus on the gripper? Really?
Yeah, this is my proposal. So,
I think the best choice is to, you can do similar things, but avoid the similarity. Because I have seen Professor Jerry Ling's work so many times, right? Every year, from the robotics course, from all the international conferences, I saw them. So I kind of know what he has been working on. So, and to be fair, I want you guys as a group in the team and then use this 3 weeks or 4 weeks and then propose something new, and then that is good for the course. And of course, hand-eye calibration is really good. But try to avoid issues. Because definitely there's something that has been built already in your lab. Don't take it. Because you take something from some other people's work, that's not your work. That's not the work coming from the course. That's not the work coming from the team. It's like relying on, you're standing on someone's shoulder for the course. But you are not supposed to do that. You're here taking the course, you are here to propose something new, based on the discussion of this team, some of you are knowledgeable because of what you have done from your lab. So that doesn't mean you can just grab some sequence of codes and then just do it quickly. We don't want that. Then some other members who are not from the lab didn't learn anything. Whoever is from Jerry Lee's lab learned a lot, or just they don't even, you guys don't even learn. Just change a little bit, okay, the project started. We don't want that. So please think about how it doesn't need to be journal quality research.
Okay, so yeah, so I have the same opinion as Professor Bobby. So maybe you can focus on because you say the difference is IEN and the other one is the eyes is separate. So maybe you can focus on the more of the hand-eye calibration. So because maybe in your lab is focused on this computer vision and all that stuff, and maybe you can, in this course, maybe you can focus on the other parts of this project. Is maybe more on the robotics side. If you can figure out what is the IEN problem, and you can solve the problem if you want. Because as actually my master thesis is doing the IEN, and I solve 7-degree of freedom robotics on, and I put the camera on it, and I solve it's all about the transformation matrices. So you can solve that. Yeah. So I think that there's a lot of things you can do in these projects, and because in your lab is more focused on the computer vision, maybe you can do the other parts. Yeah. On the robotics part. So maybe you can think about it, and also as you mentioned, you can add a gripper or other stuff. But I think if you want to do a hand-eye calibration, and you can have the robotic model you by yourself, and you use the camera and eye in hand, and you solve all the transformation matrix, and I think that will be, and so by this, then your member from other lab can involve this.
Yeah. So I mentioned about the difference is I use the camera on the robot camera, and other people use the camera fixed range. So it's different. So I can calculate the transformation from the camera to the robot.
Yes. So like because in this course we talk about how you build up the modeling of the robots, and maybe you can build, I mean theoretically, and you can build up the mathematical models of the robots and your translation of this camera eye system, and you can test it because you have the robots and you have the camera. So you can do the experiments. So I think that will be so maybe not focusing really so much on the CD problem, because I don't think everyone in your team knows that's the C computer vision, and also we didn't teach any computer vision technique in this course, so I don't think your member can be involved in this project. So if you do the other parts of these projects, maybe your teammates can be involved, and you all can learn something about it. Thank you for your all presentations, and the proposal depends on your presentation and also from your project, from your reports. So, and I think you only have around 2 months before your final presentations, and maybe you guys need to reschedule. If your M is too big, maybe too large, maybe you need to reschedule it and really think of what you can do and what you can present in these 2 months. Yeah. So I think most of you guys, your group, have done very well. So just change little bits, and you can have some really solid solution or really solid results on this project.
And also, I want to add on for the groups who are going to simulate. If you are using, for example, a MATLAB, and of course MATLAB is a really good tool for making drawings based on whatever coordinates or drawing commands, but it doesn't really represent physics, right? So you are basically providing information about the coordinates of everything, configurations of everything, and asking MATLAB to make a drawing. So it doesn't really simulate the real dynamics or friction relationship between the robot and the floor or things like that. So I know it's challenging. If you can find any physics simulating software, you can do so, but we didn't teach you how to do it. So, but sometimes when you get a package from the internet, it's like you have nothing to work on. So I know it's very tricky. So maybe you can make proper assumption in your codes. And let's say if there are some groups who are trying to simulate multiple legs, robots with multiple legs, and someone mentioned usually you need at least 3 different legs staying on the floor, the other legs trying to move forward or changing directions. So the interfacial relationship between the leg and the floor is quite important, and you can assume there's no slippage. So with that assumption, that means whenever your leg has contact with the floor, it's contacting well, so you don't slip. But maybe when you miscalculate something, and in fact, multiple legs actually truly slide on the floor, that could cause an issue, because your original assumption was to say there's no slippage. But in fact, in your calculation, maybe one of the legs truly move horizontally and then trying to slide. In that case, maybe that breaks your assumption and then that causes an issue. So there will be things to worry about if you are trying to simulate on your own, and you need to write certain rules for the physics. And once you do that, you don't want to break the rule by yourself. Otherwise, something unsuccessful will happen. So please figure out what to do. I know one of the team tried to simulate the quadratic Bezier motion for the 6-leg robot, right? So I think that is a nice simulation, but that doesn't represent the whole robot. And of course, you can try to do that 6 times and put them together in the 3D space of MATLAB, and then you can see 6 different legs doing this. But that doesn't mean walking. It's like you are just playing a sequence of this kind of motion. Right? So it still doesn't really show how moving like this in a sequence allows you to walk. So that's something to look into. Please go ahead and figure out what to do. Okay, that's my suggestion. Okay, so starting from next week, I think it's my turn. Still 2 weeks. 2 weeks from now, I will be introducing several practical examples from my lab. So some of the works that we try to focus on will be introduced in my later presentation. So I will try to show you more about the theoretical part in those research. So you can kind of use it as an inspiration for your project. Okay, and, but for the following semester, I think the most important part would be your project. You guys, that project is very important because I think it takes it covers 50%, 40%. It's a lot of percentage of the score. So please spend some time on it. And this time we have only 6 groups. Every group has many people. So please try to distribute the workload. I noticed in some of the groups, it seems like there is 1 or 2 key persons who are running the project. Whenever we ask a question, that person come up and answer. Then we know, okay, you are the guy. So it seems like there's someone hiding behind. Whoever hides behind are like the people who just share the presentation loading, like 1/5 of the loading for presentation. That's all. We cannot see his contribution. So later I'll try to teamwork more effectively, and maybe at the end of the semester when you do your final presentation, try to show who has done what as a team. I really want to see teamwork, and also it's okay to prepare notes and also to read something, but trust me, that's not the best way for presentation. It's okay to shorten whatever you want to talk about. You don't need to read the whole paragraph or write down the whole paragraph and read it. It's not the best way to present. So maybe for one slide. Usually in my personal experience, usually one slide I give 1 minute to one slide. So think about what do I want to talk about in 1 minute. Maybe only 2 concepts, or even just 1 concept. So maybe I just need to say 3 sentences, then I can cover the 1 concept in that 1 minute. Because sometimes when I talk, I think and talk at the same time. So I don't tend to talk too fast. My talking speed is slow compared to other presenters. I noticed some presenters over here, they talk super fast. You guys talk really fast. Right? So you talk really fast. So the Taiwanese, I know you guys cannot speak English in a very fast speed. So don't you try to speak a whole paragraph. Just say 3 sentences or 5, but don't tell us about what's the necessary information for that stuff. So if you can have a good practice as a student, later on when you defend for your own thesis or somewhere else, that should be good for you. Okay, so I hope this is helping, and that's it for today. That's it. Okay, thank you guys. Thank you.